Okay, here we're going to start a new topic. It's called probability distributions, specifically discrete probability distributions. And we're actually going to break this discussion up into a series of videos, something a little bit smaller. We're going to start first by introducing the concept of a probability distribution, specifically a discrete one, and again, reviewing the notation. From there, we're going to look at a concept called expected value. And that's going to be a new way for us to analyze the mean and the variance of a population based on sort of what we expect will happen based on these distributions. That'll segue us into a good conversation about risk and this concept called risk neutrality and what kind of risk taker are you, again, stemming from expected value and expected variance. Next, we're going to then segue into a discussion on two of the more common discrete random variables called the binomial distribution and the Poisson distribution. Again, those are considering what a specific random variable, a discrete random variable might do. And we'll talk more about those. So this will be a series of smaller videos that will all combine into essentially Chapter 5, or discrete random variables. So we'll jump right in. What is a discrete probability distribution? And if you watch the homework video beforehand, this might be a bit of a review, but either way. The discrete probability distributions, those are a list of values of a discrete random variable, so a countable quantitative random variable, and the associate probabilities that go with each of them. Now, in the video, we looked at them as a mass function, so the probability of a particular event occurring, but we can also look at them as well in terms of a cumulative distribution function where we look at everything leading up to that particular value. So we saw in the video the probability of rolling anything from 1 to 6 on a 6-sided die is equal. Each one of them is 1/6. But if we looked at the cumulative distribution function, we could then say that the probability of rolling a 1 is 1/6. And every time I keep going up, so probability of rolling something less than or equal to 2 would be rolling a 1 or a 2, so a 2/6. Probability of rolling something less than or equal to 3 would be the probability of a 1, 2, or 3, so 3/6, and so on and so forth. We've seen this cumulative distribution idea numerous times with frequency. Now we're just using it in terms of a distribution or a discrete random variable. So this concept shouldn't be anything new. We're just adding everything up leading up to that particular event. But we just want to be, again, comfortable with this notation where we're looking at the probability of an event occurring, of that random variable being that particular event, like rolling a 3, or leading up to it, like rolling something less than or equal to 3. So we'll do an example just to get comfortable with this. So Professor Sanchez has been teaching principles of economics for over 25 years, and he uses the following scale for grading where you can get an A, B, C, D, or an F. Those numerical scores, if you were going to do maybe GPA 43210, and just through experience, he's saying that the probability of getting an A in his class is 0.1. The probability of getting a B in his or her classes is a 0.3, 0.4, 0.1, and 0.1, respectively. So this is a traditional probability. This is a discrete probability distribution, specifically the mass function, where every event is equal to that. What we can do is display this as a graph instead of as a table, and that will let us see whether it's symmetric or not. We can then also convert these probabilities into a cumulative distribution. So what would be the probability of getting something like at least a B or at least a C or even just passing? And we'll see that here. So if we look at the probability distribution as a table, we can see that it is roughly symmetric. It's sort of curving up towards this C value. It might be a little bit skewed in the positive direction, a little bit skewed to the right, because we see that there's a bit of a drop off with the D and F. But for the most part, it's centered around this C value. And then from here, if I can create my cumulative probability distribution, so the probability of getting an A is still 0.1. Probability of getting anything at least a B in this case would be the probability of an A plus the probability of a B, which we saw was 0.3. So 0.1 plus 0.3 is going to give me 0.4, so the probability of at least a B. And then if I keep going, the probability of at least a C is 0.8. It's the sum of the probabilities of A, B, and C. So 0.1 plus 0.3 plus 0.4 is equal to 0.8. Continuing on, the probability of a D is 0.9. So that's the probability of just passing in general. So you have a 90% probability of passing. And then the F would be all possible grades here, hence why that is equal to 1. All right, so when we look at discrete random variables and we look at discrete distributions, the one concept that really continues to come up is this concept of expected value. We've been calling it the population mean, and the notation for that does not change. It's still that mu, but it'll also use this E of X value. It's an expected value. Now, what this expected value is doing is it's considering the weighted averages of all possible X values if I were to keep this experiment going for infinite number of times. So if I were to run an experiment an infinite number of times, this would be the value that we would expect to get. And we'll do a problem to really drive this point home. But what we're doing is using our law of large numbers, that if I were to continuously do this experiment, whatever it may be, it would be what I would expect for an average. And you notice that the equation for it is very similar to the average equation in that we're adding up all of our data points, but we're taking those values and we're multiplying by their corresponding probabilities. So if an event is 20% likely to occur, we would multiply that event by its probability and add all of those up. And again, I think this will be a bit clearer when we do a specific example. And then similar to the variance, when we looked at the population, same kind of idea where we're comparing it, how far it's drifting away from the mean itself or the expected value. So if I wanted to calculate the variance, I could do the same idea, see how far away each data point was from the mean, similar to how I would normally calculate variance or standard deviation, and then multiply again each one of those by their corresponding probabilities, because that would then give me a good understanding of what is the likelihood that a certain data point is further away from the mean. And it provides, again, different weight for the probability of each event. So if something is more likely to occur, that would give it a higher weight in the variance. Things that are less likely to occur will give a smaller weight, which is sort of what we would want. So let's look at an example and really see what this can do. So let's say we have this schmoozer, Brad Williams, and he's the owner of a large car dealership in Chicago. Brad decides to construct an incentive compensation program that equitably and consistently compensates employees on the basis of their performance. He offers an annual bonus for $10,000 for superior performance, $6,000 for good performance, $3,000 for fair performance, and $0 for a poor performance. So those are his bonus structures. Based on prior records, he expects an employee to perform at a superior, good, fair, and poor performance levels with probabilities of 0.15, 0.25, 0.4, and 0.20 respectively. So this is all described in this table here. So the probability that someone will get a $10,000 bonus for superior performance is roughly 0.15. The probability of getting a $6,000 bonus is 0.25, so on and so forth. What we want to do here is determine and interpret the expected value and the variance that's going on here, the variance of the expected value. So what we can do is, using our formula that we discussed, we're going to essentially look at each data point, multiply it by its probability, and then add those up. So if I have a $10,000 bonus, the probability of me getting that bonus is 0.15. So the product of those two things is 10 times 0.15, or 1.5. And we can do this for every one of these different data points. So 6 times 0.25, that 3 times 0.4, and then 0 times 0.20 is just 0. The sum of all of those is 4.2, which gets me my expected value. So in this particular case, the expected value, the average bonus that this car dealer is going to have to give out, is roughly $4,200. Now you notice that no person can actually earn a $4,200 bonus in this circumstance, but what this is doing is really providing a good estimate for possibly this employer. So if he wants to figure out roughly how much Brad is going to spend in bonuses, if he has, let's say, 25 different employees, then he could just multiply this 4,200 times 25 and get a good understanding of how much money he'll need for bonuses. So that's why expected value can really help us out here, because it can provide an average bonus for this particular person. It provides an average amount for my data points in a discrete probability distribution. So if I know essentially the value and I know the probability of that event occurring, I can use those two facts to create an average for the population. Now for the variance, I'm going to use that 4.2, and now I want to see how far each one of these data points is from that particular average. So to find that, again, I'm using this formula where I take each data point and subtract away the average, the expected value. I square those and then multiply each one by the probability, again, giving various weights to those particular things. And this is similar to how we would calculate variance and standard deviation. Just now we have this added bonus of knowing the probability of a particular event occurring. So you can see the math laid out on the far right side here, where I'm taking each one of these points, subtracting away the sum to see how far away it is from the mean, and then multiplying it by the probability. The sum of all of those is equal to 9.97, which is the variance in this case. And just like I would for a regular variance to find the standard deviation, I could take the square root of that, which would give me this 3.16. So this data set has an expected value of $4,200 with a standard deviation of roughly $3,160. And what's great about all of these then is that we can then use this expected value concept and this what you would expect for the long-term haul in things like determining risk, which will be what the next video really focuses on.